This video addresses creating frames for the FANUC robots. There are three frames that the user can create. The first frame is what they call the user frame, the tool frame, and then the jog frame. So the frames all actually use the Cartesian coordinate system. It's a user-defined frame. The default frame is the world frame. The world frame is defined as being where the first axis and the second axis or joints actually intersect. So the world frame is kind of like if you consider the robot arm like a person, it would kind of like be in about the small of your back there. So it's in a place that is really unreachable by the robot, but it's kind of the centered world frame. And it is actually considered a user frame. It's user frame 0. And you can actually create all your programs using this world frame. And actually a lot of companies do that. They don't mess with other frames. But the advantage of using a user-defined frame is the fact that you can shift that frame anywhere, and if something was to happen that the frame got the work area got shifted a little bit, or you had to shift where the actual product was that the robot needed to work on, you can just shift the frame a few millimeters and then the program will work just the same. Right. So when we create programs, we'll be creating programs here in a week or so. When we start creating programs, those points that we create inside of the program all have both a user frame and a tool frame associated with them. Now all these points in the program, they're all based on the tool center point. So we have to teach the tool frame, and the tool frame is tied to your actual tooling. And so when we talk about a point in space, that point in space is from the end of arm tooling center point, so the tool center point. And from the distance there in the world frame is to the origin, which is kind of like that small of the back of the arm kind of piece, to that tool center point. But we can shift that user frame point of reference to be somewhere more convenient. By default, the R30IA controller provides 9 user frames, and then the world frame, which is user frame 0. So you have a total of 10 user frames that you can use. So the world frame is kind of considered user frame 0. So you really have 10 user frames available to you. The active frames can actually be changed within the program. And I recommend that at the beginning of each program you set both your user frame and your tool frame at the beginning of a program to ensure that you are in the correct frame. And you can change these, so you can change these user frames on the fly within a program, but only one will be active at a time. So the command to change this, we'll kind of see this later when we get into the programming, but the command to change your current user frame inside of a program is user frame _ num is equal to, and then you would just type in the number of that frame. just to try to give you an example of why frames are useful. So if you take a frame here, so I kind of have it, you know, looking like a picture frame, and you have, let's say you have an object such as a house. And so if you had your robot with a world frame and you wanted to get to this point at the house, you may have some crazy number, like your X position might be, you know, like, I don't know, 420 millimeters, and then your Y position might be, you know, 879.419, and your Z might be minus 382.615, and so on. So the numbers could be like just very, very awkward at best. However, if we have a user frame, then we could like set up that the X direction could be exactly 100 millimeters, and the Y direction could be 100 millimeters from this origin. And then again, if for some reason the house was moved for some reason, oops. So if the house was moved for some reason, maybe just shifted over in the X position by a little bit, then we could simply go in there and redefine the frame by shifting the frame over that same amount. So we could just kind of come in here, select our frame, and shift. We could shift this frame over that 100 millimeters or whatever that it needed shifted, and then the program, all the points within the program will be lined up again. So if your frame shifts, all you have to do, or if your object shifts, all you have to do is shift your frame, and it will and all the points in the program that you spent hours creating just get shifted by that amount. So that's the general idea of a frame. If as long as your configuration doesn't change too much, then that works fine. If the configuration of your points change, then that will then you probably still have to end up redoing your points. But if the frame is just shifted by a little bit and doesn't require a change in configuration, then it's the frames really make that nice. Okay. Plus, just programming in general, you know, if you know what your points are, it makes it really easy. You can actually just kind of punch in your points when you know that, like if you look at the house here, if you're you know, if you're going from the left corner to the right corner of the house, and you know that that distance is exactly 2 meters or something like that, you could actually just punch in the value, and it makes it very easy for programming. Or if you're using offsets, and you know exactly what your offset is from the origin. Alright, so for user frame, there's 3 methods for creating a user frame. The first is what they call the 3-point method. Then there's a 4-point method, and of course there's always direct entry. So if you know exactly where your frame of reference is, you can actually just do a direct entry method. Likewise for the tool frame, There's basically three ways of creating a tool frame. Now, when you look there's actually the 6-point has various options to it, but there's basically a 3-point method, a 6-point method, and then direct entry. So if we for our tool frame is based on our tool, as I mentioned before. And usually your tool is designed on a CAD system. So a lot of times you can actually just take the numbers directly from the CAD system and do direct entry for the tool frame. And so if you know that, that's probably the most accurate way to do the tool frame. Alright, so looking at the user frame, we'll look at the 3-point method. And basically we just have to define the origin, O, down here, and then the X point and the Y point. So if we just define those points there, so if you kind of look here, we have the origin point, which is this, center point right here. So we have this origin point, and then in a direct line from that, then in a direct line from the origin point will be our X point. Alright, so it's got to be in a straight line. And then at a 90-degree angle from that, then we need to define the Y point. Now, the points should be 250 millimeters apart, okay, which is basically about 10 inches. And again, there should be a 90-degree angle between the origin to the X and the origin to the Y to make it a perfect plane. Now, it doesn't have to be perfect, but the more accurate it is, the better that your actual program is going to be. Now with the 4-point method, the difference is that the 4-point method has a 4th point, which they call the orientation origin point. So like if we look at this example with the house here, and I've got down here my origin is right here. So I've taught this origin point and then my X and my Y, but this is the, if you think about the cornerstone of a house, the foundation of the house here, we might want to actually just declare this as the origin. So why would we use this for the origin anyhow? Why not shift the whole x-axis? Well, if we shifted the whole x-axis, we may not be able to get that 250 millimeter distance between our origin and our X and our Y. So we use a larger area so we can make that distance between the origin and the X point in our frame as wide as possible. Now that 250 number there, 250 millimeters, that was a minimum recommended value. So if you could actually make it a full meter, then your points would be even more accurate. Alright, depending on the size of your robot. If you have an LR Mate type robot, one of the small ones, you definitely you don't have a meter reach. But on the large robots that stand 8 feet tall or so, you can reach a long ways with them. So, if you could make your points a meter apart, then that'll increase your overall accuracy. Otherwise, if you can't even do 250 millimeters, I'm not saying it won't work, but what happens is as you get further and further away from your origin, then any error in your frame definition will increase as you get further away from that origin. But so you have your 3-point method. You teach the origin, the X, and the Y. But again, this 4-point method, what we can do is we can teach a 4th point, which will be the origin somewhere like on our product that we're going to be working on or something like that. So everything is, so we have a 0, 0, 0 point is right there at the project. So your numbers start out very small, and like on the right on the product yourself, you have that 0, 0, 0, X, Y, and Z are all 0 points. Now when we look at this, we have this frame, we have the X direction, we have the Y direction. The Z direction, just to make it clear, Z direction is coming straight out of the page or out of the frame toward us. Okay, so positive Z is coming straight toward us. So negative Z would be down into the frame itself. All right, so the 4-point method, we teach the 3 points, and then we just redefine that origin point. Now in the picture, since it's only a 2D picture, it looks like that origin point is in the same plane that the others are, but that doesn't have to be. You can actually have it in a completely different frame. Alright, so this is just kind of showing a new origin point in there. Alright, and as I said, if you know the numbers, you can actually just punch in the numbers. It's actually faster and more accurate if you know the numbers accurately. One other thing to say, when you're teaching your frames, you want to make sure that your yaw, pitch, and roll remain constant as much possible as you can, so that they don't change, because that will kind of shift your frame. So how do we teach this? Okay. Well, the first thing we need to do is define our origin point. And then we need to define our X point along our X direction. Again, 250 millimeters minimum is recommended. If you can do more than 250 millimeters, it's going to increase your accuracy. Okay, so it doesn't have to be exactly 250 millimeters. It can be less than that, but that's really going to decrease the accuracy as you get further away from your origin. And but it can be much more than that if you can reach it. All right, so one important thing about your frames, you need to make sure that whatever frame that you choose, you'll be able to reach all 3 of those points with the robot arm. Now, that doesn't mean that every point within your frame, like when you define that frame, if we look back at this frame here for a minute, I use this frame as a reference point to have my origin, my X, and my Y. But points way over here, if you have like a point over here, once you define the frame, this point will be defined. It'll know that this point is in a minus X direction and a plus Y direction and whatever the Z direction is. So the points, all points in space are defined once you define that frame. All points in space are defined. It knows where those are. It basically remaps them back into the world frame, because the world frame is the robot's true point of reference. And so all these points inside of these user frames are just math, and it's just a mathematical transformation to describe where they are in the world frame. Alright, so but we have to just go in and save all 3 of those points. Okay. Once we do that, we can then define that user frame as a point of reference for jogging and in our programs. So what we need to do to get into frames, the first thing we would need to do is go to the menu key and then go to setup, which is on the first screen there, and then we'll press F1 for type. So you would press the F1 button, you see it labeled type here, and that'll get us into frames, and it'll actually show the whole list of the 9 user frames and the world frame. Now we can't actually modify the world frame, right? That's fixed. So remember that the world frame, like here's axis 1 between the yellow and the gray, and here's axis 2, which is the second axis that can rotate. So if I was able to draw a straight line up through the center point of axis 1, and then horizontally through the center point of axis 2, my origin point would be here somewhere back behind the robot. That's the world origin point. That's the focal point for the robot. And as I said before, all points are measured on the tool center point. Remember this green ball here in the RoboGuide software is referred to as the TCP globe, the tool center point. And so all points are truly measured from here, which is the origin, out in the X direction, up or down in the Z direction, and left or right in the Y direction to that tool center point. So all points are defined from the origin to this tool center point. Alright, so but we, again, to get into frames, we'll go to menu, go to setup, press F1 for type, and choose frames. Now when you first do that, you'll be at by default you'll be at the tool frame listing. So then you would press F3. Now that's on the previous screen to this one. I don't have a shot of that, but you would press F3 for other. And so when you press that, you would have your choice between tool frame, user frame, and jog frame. All right, and then it would list all the different frames that are available, and then you would select one of those frames, and you get into this frame. Now you notice up here it actually says user frame up there at the top, and then it also says that I'm currently in frame number 1. And you see the values are all zeros here. All the values are 0, 0, 0 for this user frame. And that's the default for all user frames when you first start out with the robot. And that is the faceplate of the robot. So remember, the faceplate is where the tooling actually mounts on the robot. So by default, the user frame is the center of the faceplate. And so then what we would have to do is come in and we would choose the method. So we could come in here at 2, press F2 to choose the method to teach. And this method would be, we would have our choices there of 3-point method, 4-point method, or direct entry method. Now if you get the direct entry method, then it just shows you the screen where you have your XYZ, yaw, pitch, and roll, and you just punch those numbers in. But if you choose the 3-point method as shown here, you'll have your origin point. Sorry, I can't speak this morning. You'll have your X point and your Y point, and initially those will all be listed as uninitialized. All right, now one other point to say: when you start teaching a point, in here, that point, or that, make sure you're not in when you're jogging the robot around, don't be in the user frame or the tool frame that you're going to be teaching. be in any other frame. It doesn't matter what other frame, but you don't want to be in the frame that you're teaching. I recommend using the world frame for jogging the robot around. And of course, if you need to, you can always pop to the joint mode to shift just one joint a little bit to get it lined up. All right. So then you'll move the robot to the origin point. So you see here is my origin point. I've got the robot. I'm using this blue box as my reference for creating my frame. And so I put it at the origin. So I put the robot at one corner of the box, and I'm going to call that my origin. And once I get the robot to that point, then I will do a shift and press F5 for record, and it will record that point. Then I will shift it in my X direction, which for this robot, now notice the XYZ that is showing there that you're seeing on the screen at the tool center point at the teach tool, that is based on the tool frame. That is the tool frame's X, Y, and Z because we're clicked on the TCP globe there. And so that XYZ is the tool frame of whatever tool frame that this robot is currently in, and it's not the XYZ that we're training, okay, because you can see Z is actually pointing straight down here. But we would take and move the robot to wherever we want the origin to be and do a shift record and record that point. Then we would move the robot out to the next point. So I went, in this case, I went in the plus X direction for the robot. I just had it lined up there. So I'm teaching the exact same plus X, and I do a shift and record, and you can see that the X direction point is now recorded. Now notice you need to make sure that you use your arrow keys to select the next point before pressing shift record, or you record over your previous point, and there is no undo in this. So if you mess up and you press shift record and you're in the wrong point, you forgot to move down to the X point, then you've lost your origin point. So so you have to be careful. You got to make sure that you shift your files there, or shift to the next line before you hit your shift record for your next point. Now notice the X, Y, and Z numbers have not changed, but once I select that third point and initialize it, I will have new values for my X, Y, and Z. Alright, so here I went over to my third point and I pressed shift record. Again, I came down to the Y and then pressed shift record there. Now notice it then changed. All 3 points are listed as used, and also notice that the X, Y, and Z values and the yaw, pitch, and roll values all got set. Okay, and you can see that yaw, pitch, and roll, because this is pretty much pointer's perpendicular to the box, and which is perpendicular to the ground, that the yaw, pitch, and roll are 0, but you can see that it actually kind of threw a negative on the yaw and the pitch values in there. All right, but this is my user frame, and taught using this 3-point method. Okay. All right, so this is the main screen for the user frame that you would first get into when you press the menu. And you can see here, should have probably showed you this earlier, but this is that first screen. So you can see like frames 2, 3, 4, 5, 6, 7, 8, and 9 are just all 0, which means they're the faceplate. But tool frame now, tool frame 1 now has been taught. Also notice there's a comment area, so we can actually come in here and describe this frame with a meaningful comment telling us what that frame is. Okay. But you can see these values. So when we were on this previous screen, or on this previous slide here, this is inside of the frame settings so that we can teach it. And then we hit the previous button to get back to this next screen here. All right. But one other thing I want to kind of mention here, you see there F4 is labeled move to in here. Once you teach these points, even if you only have one point taught, you can use the move to button to move back to that point. Now I want to warn you, before you start messing with a move to, always jog the robot away from any objects. So because move to is going to use the joint movements, and it's an unpredictable path. We don't exactly know what direction or what path. We know where it's going to go to because it's going to go to that point that we just recorded. So we know where it's going to end up at, but we don't know the path it's going to take to get there. So you always need to make sure that you move the robot, jog it back up and out and away from any objects that it may run into, so that you can see that it has a clear path to move back to that point before pressing the move to. And then also kind of keep your finger near that hold key. All right, remember the hold key here. So anytime you're doing a move to, if you press the hold, it will then stop the robot in a nice, smooth, controlled manner. Of course, if you have to, if it's an emergency, you can always release the dead man. But that is harder on the robot because it's actually slamming on the brakes. So it's a nicer thing if you need to press the hold button. Also monitor your speed, because it's going to move at whatever speed setting that you currently have your joint teach pennant set at. So if you look up here in your screen, you can see that this robot is currently set to 100% speed. Now, since we're jogging, that's 250 millimeters per second, but that's still pretty fast. So, I don't recommend doing any jogging or moving to at 100% speed. All right. So, anyhow, this slide here is showing the XYZ. This is again just in Robo Guide. We can't actually see this on the Teach Pennant. This bottom part that I got highlighted here is only for Robo Guide software, but it's showing you XYZ, which is basically the world frame, and it's showing you that the user frame is defined, as I mentioned before, based on the world frame origin. So these numbers, this 399 minus 101 and minus 130 numbers for the user frame are based on the world frame setting. And we can also see like the yaw is minus 180 because it's pointing straight down. And so that's why that yaw value is there, because it's based on the world frame. So all these locations and stuff are based on that world frame. Okay. All right, now on the robot itself, remember, we can always press the position button and we can see those values. So we can always see based on the joint settings, the world frame, okay, we can always see those, and whatever user frame we're currently in. So again, notice up here on this screen, because when we select the user, we selected the user setting up here, and then we have frame 1, so it tells me which user frame I'm in, and then it also tells me what my current tool frame is, because all points are tied to that tool frame. Now tool frames depend on what tool that you attach. So every time you attach a tool, you need to make sure that you teach that tool frame. If you don't, then again, it's tied to the faceplate, which is not going to be correct once you've attached a tool. Okay. Um, all right, to select a new frame for jogging, or to just set it before we create a program, we can press the shift button and then the coordinate key, and it'll pop up a little menu, and in that menu we can set our user frame, our tool frame, or our current jog frame. All right. Now, one thing about jog frames are only for jogging the robot. So as I mentioned earlier, every point in a program, unless it's stored as joints, is stored based on the user frame and the tool frame. All right. But the jog frame is only for jogging the robot. So if you have a tight space that you need to move the robot through, you might want to create a jog frame so that as you're jogging it, instead of some weird direction, you can just do like a plus or minus Z to move straight in and or out of this kind of weird angle sort of thing that you have to move to or something. So jog frames are basically like a user frame, but they're only used for jogging. They're not part of any program. Okay. Now, the only difference with the 4-point method is we have a system origin point. So this new origin point marked up here, you can see the big blue there. That is the system origin point. And so you teach the first 3 points just like you did for a 3-point method, and then you just move it to wherever you want to call 0, 0, 0 at. And that is the 4-point method. Okay. Now, tool frames are based on the tool center point, and so it depends on what kind of tooling you have. So I'm just in this slide, I've got several different tools here, and each one of them would have a different tool center point. You may even have some tools that are kind of like a double tool. A lot of times, especially for picking up product and putting in, say, a CNC machine or something, you don't want to like have to pick the part out and take it out of the machine and then set it down and then grab a new part and put it in. So usually those tools are kind of like a double tool, so that you actually pick up the new part, pick up the part that you're going to put in the CNC machine, go into the CNC machine, pick up the part with the other side of the tool. It's kind of like a double hand thing. So you grab the part that the CNC machine just finished with, and then you rotate it 180 degrees. You set down the part that it now needs to work on, and then you pull the arm out. So this saves a lot of wear and tear on your robot, and it saves a lot of time in production, because you pick up the part that's going to go into the CNC machine, lift the part out that the CNC machine just got done with, flip around 180 degrees, so you just do a roll of 180 degrees, you have to lift up a little bit probably or something, and then just do that roll of 180 degrees, set down the part that the CNC machine is going to process next, and then come back out of the CNC machine. Now the CNC machine can start working on the newly placed part, while the robot is placing the finished part down on the conveyor to be sent down to the next process in the line. All right. So, but the tool frames are based on that tool center point. Okay. And again, we have, just like with user frames, we have 10 frames that can be used. And you don't want to be in any of those frames when you're teaching them. All right. Now, the tool frame uses what they call the left-hand roll. So the user frame, I didn't mention that in this video yet, but the user frame uses the right-hand roll for X, Y, and Z. The tool frame uses the left hand roll. And remember, plus Z, when you're in tool frame, plus Z is pointing directly into whatever way that the the tool is pointing. And if we want to put in our program, when we get into teach-dependent programs, I really think that we should always start our user frame and user tool numbers. We should start the program by defining what frames that program is starting with. And remember, a program could change these frames later on inside the same program, but you should always kind of put the U frame number and the U tool number at the beginning of your program so it knows what frame it's going to be in. So again, the three base methods for tool frames are 3-point method, 6-point method, and direct entry. So for user frames, you have a 4-point method. For tool frames, you have a 6-point method. Okay. All right, so what we need to do when we're teaching a tool frame is we need to make sure we have, instead of an origin, an X, and a Y, we have what they call approach points. Okay, and these approach points need to be perpendicular to each other, or at least as close to perpendicular as possible. All right, so here we have a robot, and I'm trying to teach, this is in the course in the RoboGuide software, and I'm trying to teach a point in space. So what I've found is that you want to have a sort of reference point to teach that point in space. So you see here, I've taught this first point, and I've taught it perpendicular, coming straight down to my reference point. Now notice the reference point itself doesn't matter. The reference point could be anywhere in space. Okay, so it doesn't matter where this reference point is. Where with the user frame, when you know that origin and the X and the Y, those points were defining that plane, and that origin point is the 0, 0, 0 for that user point. But for a tool frame, your frame of reference is that tool, that tip of that tool. And so it doesn't matter exactly which point you pick in space. But so notice here that I placed the robot here, and I'm just kind of highlighting here that my roll is 0 here. And so then when we look at the next point now, this is a quick way of doing this. What you can do is you had your first point, here, and notice in this example my roll was perfectly 0. That isn't always the case. Your roll may be 37.9 degrees. But when you teach your next point, this is kind of a quick way. Remember, it has to simply be 90 degree. These are approach points to this point in space, and they have to be 90 degrees apart. So what we can do is we can actually just manually jog the robot 90 degrees from this other point. So if this point wasn't perfectly 0, that's fine. Just add 90 degrees, or if you need to, for some reason, you can subtract 90 degrees. It doesn't matter which way you go, but just change your roll, just jog that 90 degrees, either just change your roll plus or minus 90 degrees, and that will set your second point. And then you just do a shift record, and you've recorded your second point. Now your third point's a little tougher. You've actually going to have to rotate the robot down and come at a different plane, because we need to have it perpendicular to both point 1 and point 2. So you have to come down at a completely different angle. So it takes a little more work to get that third point in the tool frame. You gotta kind of twist that down and come straight at an angle. And again, when you do this, you have to make sure that the robot can get to it. So sometimes, like this one's going down to on the right side of, based on the robot's reference, or on our reference, kind of looks like it's on the left of that point. But in a lot of times when we may not be able to reach that, so maybe we have to come down at the right, and it doesn't have to be perfectly left or right. It just has to be perpendicular to the plane of the other 2 points, which were more of a vertical point. So you just want to bring it down and come at it horizontally, but it doesn't matter exactly where horizontally that you decide to come at it for your 3 points. But these are approach points. These are how you're coming into it. Okay. So that's the 3-point method. Okay, that's the 3-point method. We come straight down, and then we rotate 90, and then we kind of have to flip and come horizontally. Okay, and again, it doesn't have to be perfectly vertical and horizontal, but it sure makes it easy teaching them if you make them that way. The 6-point method, what the other 3 points are for the 6-point method, is they allow you to redefine the directions of X, Y, and Z. Now, normally by default, when you're in the tool frame reference, plus Z is, as shown in this slide, coming straight out of the pointer of the robot. However, it doesn't have to be. So what the 6-point method allows us to do is redefine an X, Y, and Z direction for our tool frame. Alright, so for this 6-point method, we go in here and we simply, the first 3 points are just what we did before. But then we're going to pick, kind of like a user frame, we're going to pick an origin point, an X point, and a Z point. Okay. Now again, that depends on your version of the software. You also may have an X and a Y choice. But these 3 points, you should be 250 millimeters away from the origin, and they need to be perpendicular from each other when you teach those. So depending on your version of the software, you may have a couple of different choices for 6-point methods, but the 3, whichever one you choose of those, you're always going to define that origin point, and then an X direction, so many millimeters. It should be at least should be, this says of 200, oh, it says minimum, yeah, minimum of 250 millimeters from the origin point. And then one other thing, when you're teaching user frames, you should always kind of return back to that origin before you start in the next on your Y direction for user frame, or so once you teach the X, I always move the robot away from there and use that move to return back to my origin point, and then move in the Y direction if you're in user frame, or if you're using the Z option for the tool frame, then shift it there. But always return back to your origin point before trying to teach the next point. Alright, so finally, just again, I want to mention the jog frame. A jog frame, you teach it, it only has a 3-point method or direct entry. It doesn't have a 4-point or a 6-point, and again, it's only used for jogging. Alright, so we have basically 3 types of frames: the user frame, the tool frame, and the jog frame. When we are in jog mode, remember that we can also, we have the world frame, which is actually user frame 0. So when I say user frame, I could be talking about the world frame if I'm not being very precise, because world frame is user frame 0, so it is considered a user frame. But when we're jogging the robot, we also have the joint mode that we can jog in. So technically, joint mode's not really a frame. It's just saying I'm going to jog one joint at a time. But the user tool and jog frames, we can, when we jog in those frames, we might be moving all 6 joints at the same time, depending on how we're trying to move it. But these are our frames of reference. The user, every point, when I teach points in a program, as we'll be starting programs here soon, and every point, when you teach a point in a program, it's going to be associated with your user frame and your tool frame that you taught that point in. And so you have to be careful in there, especially in the classroom. What we run into a lot of times is when you go up to work on a robot, you might be assigned user frame 5, but one of the other students, the student before you, had user frame 4. And then you go up and you start teaching your program, and then all of a sudden you find out that that the robot was set to user frame 4, so now all your points are defined in user frame 4, not your user frame, and so they're all wrong, and you have to reteach every single one of them. All right, and so that's kind of why I mentioned in here, I highly recommend you start every program by defining your user frame and your tool frame, and start those in your program, and then always kind of execute those or verify that you're in the right frames before you start teaching points, because it happens so often that somebody goes through and they spend half an hour or an hour teaching a program, and then they find out that every single point that they taught is wrong. And so now they've got to go back and reteach every single one of those points, which is very time consuming. So before you start saving points in a program, always make sure that you're in the frames that you want those points to be saved as, because when you record those points, the frame, both the user frame and the tool frame, is stored as part of that point reference.